Hello everyone. Today we're going to be going over an example problem that pertains to utilizing the conservation of mass and the first law of thermodynamics for an open system. For this particular problem, we have air entering a compressor at 100,000 Pascal, 293.15 Kelvin, through an area of 0.15 square meter, and at a velocity of 30 meters per second. The air is compressed, and upon exiting the compressor, the air is at a pressure of 1.8 times 10 to the 6 Pascal, a temperature of 673.15 Kelvin, and it exits the compressor through an area of 0.08 square meter. Okay, so I've already gone ahead and listed all of the knowns that we have for both our inlet and our outlet, as well as the individual gas constant and the specific heat at constant pressure for air. Okay, in terms of assumptions for this particular problem, since we're dealing with air, we do have a compressible substance. And therefore, our equation of state for this problem has to be ideal gas. So we're going to be assuming ideal gas for air. We're also going to be going ahead and assuming that we have a steady state problem. And we're also assuming that our compressor is very well insulated and adiabatic, and therefore adiabatic. And as a result of this, we have no heat transfer coming in and out of our system. So our Q dot is just going to be equal to 0. Okay. Now this problem asks us, what is the amount of power that we have to put into our compressor in order to achieve this change of state from the inlet to the outlet conditions? Okay, so let's go ahead and get started on our solution. Now, with open system problems, I generally always start with the conservation of mass. The reason why is if the mass flow rate's not known, I can go ahead and calculate the mass flow rate, which is something that's very convenient to know, especially when going into the conservation of energy, or the first law of thermodynamics for an open system, and also might be able to help us determine other things that we might not know, such as velocities or areas, etc., depending on the problem. So let's go ahead and see what the conservation of mass tells us for an open system, for this open system. So we have dm Cv dt is equal to our inlet mass flow rate minus our exit mass flow rate. Now we already went ahead and assumed that we have a steady state problem, and therefore our dm Cv dt can just assume to be 0. As a result of this, conservation of mass for an open system tells us that our inlet and our outlet mass flow rates are equal to one another. So therefore we have m dot 1 equal to m dot 2, which is just equal to some constant m dot. Now recall that the definition of a mass flow rate is that we have density times velocity times our area. So our mass flow rate is just equal to density times velocity times area. Now, if we go ahead and look at the knowns that we have for our problem, we actually know quite a bit about our inlet conditions. We know its velocity, we know the area, and we also know temperature and pressure. So upon seeing this, we can go back here and we can actually see that we can actually calculate the mass flow rate with all of the knowns that we have for our inlet conditions, because we have the velocity, we have the area, and using temperature and pressure and the individual gas constant, we can figure out what the density is at the inlet. Okay, so let's go ahead and calculate the density, or derive the expression that we can use to calculate the density at the inlet. So we're going to go ahead and use our ideal gas, which is one of the assumptions that we made previous at our inlet conditions. So we have P1 is equal to rho 1 R T1. Now if we go ahead and solve this for rho, we get rho 1 is equal to P1 divided by R T1. So now what we can do is we can take this expression and plug it into our mass flow rate at the inlet conditions. So what we end up getting is m dot is equal to, so rho 1 V1 A1 is equal to P1 V1 A1 divided by our T1. So here's our expression in terms of all properties that we know for our system at the inlet condition. And using this, we can calculate our mass flow rate. So let's go ahead and plug in all of our knowns. So we have our pressure, we have our velocity, we have our area. This is all divided by our individual gas constant, so 287 joules per kilogram in Kelvin, and our temperature, so 293.15 Kelvin. Now when we go ahead and calculate this, we get that m dot is just equal to 5.35 kilograms per second. Okay, so now awesome. We know our mass flow rate. We've actually gathered quite a bit of information using the conservation of mass for an open system. We know that the mass flow rate has to be the same at both the inlet and the outlet, and we also know what that mass flow rate is. Okay, so let's go ahead and take a look at the conservation of energy, or the first law of thermodynamics for an open system. So we have dECV dt is equal to Q dot minus W dot plus our inlet mass flow rate times our specific enthalpy plus 1/2 V squared plus GZ, evaluated at our inlet, minus our exit mass flow rate times our specific enthalpy plus 1/2 V squared plus GZ, evaluated at our exit. Okay, so now let's go ahead and take a look at each of the terms and determine which terms stay and which terms can go. Okay, so going back to our assumptions, we already said that we have a steady state problem, so our dCV dt term is just going to go to 0. We also said that our compressor is well insulated and therefore adiabatic, which means that we have no heat transfer between the surroundings and our compressor and vice versa. So our Q dot is just 0 as well. Now, since our compressor isn't moving up and down or falling from the sky, etc., we have no change in potential energy, and therefore our GZ terms can also be neglected. So we're going to neglect potential energy changes because there is no change in potential energy for this particular problem. So what this leaves us with is we get minus W dot plus M dot 1 times H1 plus 1/2 V1 squared minus M dot 2 H2 plus 1/2 V2 squared. Okay, now recall from our conservation of mass, we have found that m dot 1 is equal to m dot 2, which is just equal to some m dot. And as a result of this, we can go ahead and not only solve this expression for w dot, but we can also reformulate it into a much simpler form. So we get w dot is equal to m dot times the change in our specific enthalpy, H1 minus H2, plus 1/2 times the change in the square of our velocities. So V1 squared minus V2 squared. Okay, so to the change in specific enthalpy. Now recall from lecture that we can actually find, for an ideal gas, the change in specific enthalpy by means of delta H is equal to our specific heat at constant pressure times the change in temperature. So just plugging that into our expression, we get that the power is equal to m dot times Cp T1 minus T2 plus 1/2 V1 squared minus V2 squared. And there's our final expression to calculate the amount of power that's required for us to put into our compressor in order to change the states from the inlet to the outlet conditions. Now, let's go ahead and tally each of the quantities or each of the properties that we know for our system and determine if there's anything that we need to calculate before determining the power. Okay, so m dot. We know m dot because we found that in step 1. We also know our specific heat of constant pressure because that was something that was given to us in the problem statement. We also know our temperatures. That was also given to us in the problem statement. And we're also given our inlet velocity. But we do not know our exit velocity. So this is something that we have to figure out. And that is going to be our next step, step number 3. So what is V2? So how can we figure this out? Well, we can do this actually just by our mass flow rates. So in step 1, we found out that by conservation of mass, that the mass flow rate at both the inlet and the outlet have to be the same. Now we can utilize this piece of information in order to help us calculate what the velocity at the outlet has to be, because we are not only given the temperature and the pressure to find the density at the outlet, but we're also given the area. So since we know m dot, the temperature, the pressure, and the area at the outlet, we can figure out what the velocity is. So let's go ahead and do that. So we get m dot is equal to rho 2, V2, A2. Now by ideal gas, we get P2 is equal to rho 2, our T2, and we can rewrite this in terms of just solving for our density at state 2 at our outlet, or state 2. We get P2 divided by our T2. So taking this expression and plugging that back into our expression for our mass flow rate, we get m dot is equal to P2, V2, A2 divided by our T2. Let's go ahead and solve this for V2. And what we get is m dot r T2 divided by P2, A2. And we know all of these properties. We know m dot, we know the individual gas constant for air, we know temperature, pressure, and the area at our outlet. So let's go ahead and plug in our known properties and calculate the exit velocity. So we have our mass flow rate, we have our individual gas constant, we have our temperature, all divided by our pressure. Let me rewrite that. That was probably hard to read. 1.8 times 10 to the 6 Pascal times our exit area, like so. Okay, so now when we go ahead and calculate this, we get that our exit velocity is 7.18 meters per second. So we now know both our inlet and our exit velocities. Our inlet velocity was 30 meters per second, and now we know our velocity at our exit, which is just 7.18 meters per second. Okay, so now we know everything that we need to know for the expression we derived in part 2 to find the amount of power in order to change our state from our inlet to our exit state, or our inlet to our exit conditions. Okay, so what we have, plugging everything into our expression for power, is power is equal to 5.35 kilograms per second times our specific heat at constant pressure for air times our temperature difference let me rewrite that a little bit. No, okay, that's that's kind of better. Okay, plus 1/2 our v1 velocity squared minus our v2 velocity so the difference in our square velocities and when we go ahead and calculate this, what we end up getting is minus 2.0836 times 10 to the 6th watts. Or we can rewrite this in terms of kilowatts as minus 2083.6 kilowatts. And that is our final answer. So that is the amount of power that we have to put into our compressor, and keep in mind the negative sign denotes that the amount of power is going into our system, so our sign convention works perfectly. So it physically makes sense why we have a negative sign. So it's the amount of power that we have to put into our compressor in order to achieve the change of state from our inlet to our outlet that we're seeing through our compressor. Okay. So in general, these open system problems pretty much run the same course. So it's going to be, start conservation of mass, figure out everything that you can using conservation of mass, and then move into conservation of energy, or the first law of thermodynamics for an open system, and find out everything that you can using that. So it's a lot of these problems are just really a partnership between conservation of mass, the first law of thermodynamics, and your equation of state, depending on if you have an ideal gas or an incompressible substance. In general, for all of these problems, I follow the exact same steps, which is just conservation of mass into first law of thermodynamics, and you can really see how the problem is supposed to evolve in order to solve the quantity that you're looking for, the property that you're looking for. Yeah, the property or quantity, we'll say. Okay. So that was the solution for this particular problem. I hope the solution was helpful. If you have any comments or questions regarding any of the steps or the assumptions that I've made in the problem, feel free to leave a comment below, and I will do my best to respond to them as quickly as I can. Again, thank you for watching. I hope this was helpful, and I will see you next time.